This is Physics 2211 Lab 4 Oscillations. The purpose of this lab is to compare the motion of a mass oscillating on a spring both computationally and experimentally, as well as plot the changes in energy that occur throughout that oscillation. The results we get are that the models are strikingly similar, especially in the x direction, and that the energy is conserved as the system is isolated, so the total change in energy is equal to zero. The models used in this lab are both computational and observational. The methods used are tracker, which was used to quantify the change in position of the object by determining the position frame by frame, GlowScript, which was used to computationally iterate, and Excel. As for the physics principles used within this lab, we use Newton's second law, which is the momentum principle. This states that the net force experienced by a system is equal to the system's change in momentum over the change in time. From this, we derive the position update formula as well as the velocity update formula, which are both used within the GlowScript code. We also use the energy principle, which states that the change in energy of a system is equal to the work done by the surroundings plus the exchange of thermal energy between the system and the surroundings. When using this equation, it's really important to define what exactly is your system and what exactly is your surroundings. Other energies of importance within this lab are kinetic energy, which is K equals 1/2 mv squared, gravitational potential energy, which is just mg times the displacement in the y direction, and spring potential energy, which is 1/2 ks squared, where s is the stretched length of the spring. For our observed model, we use tracker. We identify the system as the mass, spring, and earth, which means in our surroundings we have nothing. Here's our initial position of the mass. Our initial velocity will be 0 meters per second. Our time interval will be about 10 seconds, and we are shooting at 10.5 frames per second. For our computational model, we use GlowScript. First, we need to set initial conditions and constants, such as the mass of the ball, which is 0.402 kilograms, g, which is the acceleration on Earth, the spring constant, which is 6.83 newtons per meter, and L naught, which is 0.123 meters. Next, we added the values for the spring, such as the length of the spring, by subtracting the spring position from the ball position, L hat, which is the direction of the spring, so we divide L by the magnitude of L, and S, which is the amount of stretch happening in the spring. We take the magnitude of L and subtract L naught. Next, we compute energies such as kinetic, gravitational potential, spring potential, and our total E will be 0 since the system is isolated. So how we found our spring constant and L naught. For spring constant, we use the period equation for springs, which is as shown, and we solve for K. We use the tracker data to determine the length of the period, and we get 6.83 newtons per meter. To solve for L naught, we set F net equal to 0, which is static equilibrium for the mass, and we just solve for L naught and we get 0.123 meters. Continuing on with our computational model, next we calculate the net force, which is going to be the spring force and the gravitational force. Our spring force is negative Ks, and our gravitational force is mg. We then update the velocity and position according to their respective update formulas, and then we update the spring by updating the length, direction, and stretch, and finally calculate changes in energy. Here are our results for the experiment. We can see on the left is our change in energy versus time. Delta E is that straight orange line that stays constant at 0, showing our system is isolated. We can see that our spring energy is oscillating as well as our gravitational potential energy. As for our position versus time graphs, we see in the x graph that both our model and experiment showed very similar data for the x position, while the y position is also similar, but not as similar as the x position. So what does this mean? Yes, the energy principle is satisfied. The energy principle states that the change in energy is equal to the work done by the surroundings plus the change in thermal energy between the surroundings and system, which should both be equal to 0. The total change in energy is 0 because we defined our system to include the mass, earth, and spring, so there's nothing left in the surroundings, so the work of the surroundings would be 0, and the exchange of heat between the surroundings and system would be 0 as well. We can see that this is satisfied within the model because we had that straight orange line at 0, which represented delta E. Comparing our periods that we saw in the x position and y position, we get a period of 1.65 seconds in the x direction and a period of 1.49 seconds in the y direction. So the discrepancy between these two periods could be due to user error with the tracker software, such as not clicking the exact center of mass when tracking, and it could also be due to neglecting the drag force.